It sounds impossible. In 1913, workers built the Woolworth Building's 57 stories without a single functioning elevator to haul men or steel skyward. Every beam was pre-numbered miles away, and every error meant days lost. Workers climbed up to 20 stories on foot twice a day through wind and weather, just to reach their tools. Before elevators, how was a skyscraper even possible? The answer is more precarious and more ingenious than you think. Steel. For these early skyscrapers began its journey hundreds of miles from the city, at mills in places like Pittsburgh and Bethlehem. Every beam was custom rolled, measured to the inch, and stamped with a number that matched a master plan drawn by engineers in New York. These numbers were not just for show, they were the only way to keep track of thousands of pieces that had to fit together in a precise order, like a steel puzzle stacked 50 stories high. Once finished, the beams were loaded onto rail cars in the order they would be needed, column by column, floor by floor. There was no extra room for error. A misnumbered piece or a shipment out of sequence could bring the entire process to a halt. Contractors' clerks tracked every carload using ledgers and manifests, double-checking that each shipment matched the assembly schedule. If a single beam arrived mislabeled or missing, the crew might have to stop work while a replacement was located, sometimes waiting days for the right piece to arrive by rail. In the dense heart of Manhattan, there was nowhere to stash extra steel. The streets around the site filled with wagons and flatbeds, each holding beams that had to be hoisted skyward almost as soon as they arrived. There was no buffer, no stockpile, just a relentless flow from mill to rail yard to curb, and then straight up by derrick. During peak weeks, the pace was staggering. In 1912, the Woolworth Building's frame consumed more than 1,000 tons of steel in just 6 days, enough to stretch across a city block if laid end to end. But this speed depended on a supply chain that was both tightly choreographed and incredibly fragile. A delay at the mill, a rail bottleneck, or a single clerical error could idle dozens of iron workers and leave a steam derrick standing silent above the street. Developers like F.W. Woolworth used their influence to push foundries and railroads for priority service. But even the wealthiest clients could not conjure steel from thin air. On the ground, staging the deliveries was a daily crisis. With no storage space, beams had to be sorted, checked, and immediately lifted to the right spot in the frame. Clerks, often overlooked in the drama of high steel, became the silent nerve center of the operation. Their ledgers, filled with car numbers and delivery times, were as critical as any engineer's blueprint. A single mistake, a transposed digit, or a missing stamp could send a ripple of delays through the whole project. In the world of construction without elevators, the real drama often started long before a beam ever left the ground. At street level, the job site looked more like a lumber yard than a modern construction zone. Timber platforms crowded the curb, stacked with steel, bricks, and barrels of rivets. These platforms weren't just for storage, they formed a living network of walkways, ramps, and makeshift bridges, connecting wagons, derricks, and the rising skeleton above. Every morning, crews arrived before sunrise, threading through a maze of planks and sawdust, ready to start the day's climb. Permanent elevators were still months away from being installed. Until then, every worker, from riveters to masons, had to rely on their own legs to reach the upper floors. Inside the steel frame, carpenters built temporary wooden stairs, sometimes called stair highways, snaking up through the half-finished structure. These stairs were narrow, steep, and often slick with rain or dust. Workers climbed them 2 or 3 times a day, carrying their tools, lunch pails, and whatever gear they needed for the shift. On a 20-story site, that meant hundreds of feet up and down, day after day. The effect on productivity was real. Payroll logs from the era show that tradesmen lost up to an hour each day just in vertical travel. Iron workers, known for their stamina, sometimes wore through a pair of boots in a single month. There were no handrails, no safety codes, and no guarantees. A missed step could mean a fall through the open frame to the street below. Even so, the stairways had to keep pace with the steel, rising a floor or two each week as the frame grew taller. Carpenters worked ahead of the main crew, hammering new treads into place before the next wave of iron arrived. Below, the platform crews managed the constant churn of materials. Every beam, bucket, and barrel had to be sorted by number and destination, ready for hoisting at a moment's notice. The platforms themselves shifted and expanded as the building rose, sometimes rebuilt overnight to handle a new delivery or to make room for a derrick's moving base. It was a kind of choreography, timber and steel, muscle and sweat, where every step and every plank mattered. For the men who climbed, the daily ascent was more than just a commute. It was a test of endurance, a ritual repeated in all weather, from summer heat to winter sleet. By lunchtime, legs burned and lungs ached, but there was no shortcut. Until the very last beam was set and the elevator machinery installed, the only way up was the hard way. One stair, one story, one climb at a time. Steam engines pressed into service at the curb became the muscle behind every vertical leap of steel. Each morning, the firemen stoked coal into the boiler, building pressure until the hoist operator could crack open the throttle. 50 to 100 horsepower surged through spinning cable drums, wound tight with wire rope as thick as a man's wrist. The guide derrick, a timber mast sometimes 70 feet tall and stabilized by taut steel lines, stood ready to reach up and over the tangle of city streets, its boom sweeping a path above the noise and chaos below. A beam, fresh off the wagon, was chained to the derrick hook. The rigger on the ground checked every shackle, then signaled up. The hoist engineer, perched beside his steam drum, watched for the cue. One sharp whistle, and the cable drum began to turn. Steam hissed, gears clanked, and the load rose steadily, clearing horse-drawn wagons and trolley wires in its slow, swinging climb. The derrick's boom, pivoting on a massive stool, could swing a 20-ton beam from curb to frame in a single arc, if every guideline held its tension and the wind stayed calm. Guy lines anchored to the rising skeleton braced the mast against sudden gusts. Each line was tightened with turnbuckles and checked daily for slack. The rigger crew, sometimes half a dozen men, managed these lines with constant attention, knowing that a single loose shackle could send the whole mast lurching. When a heavy lift was needed, like the Woolworth Building's main columns, some weighing close to 20 tons, the crew adjusted every anchor, calculating the force each line had to bear. On the Singer Building, records show a main derrick with a 75-foot mast and a 65-foot boom, rated for 40 tons. But most jobs used 10-ton or 20-ton derricks built for speed and reliability, not brute force. As the building grew, the derrick itself had to climb. Once a section of frame reached its limit, the crew slackened the guy lines, unbolted the base, and rigged an auxiliary hoist. Inch by inch, the entire mast was lifted up to the next platform, then bolted down and guyed out again. This leapfrogging network of derricks kept pace with the rising steel, always one step ahead of the ironworkers waiting above. Hoist engineers and riggers became a tight-knit team. The engineer, hands on the throttle, watched for hand signals from the top, an open palm to stop, a circling fist to swing. With no radios, every lift depended on this silent language. The rhythm was relentless. Load, lift, swing, set, repeat. At peak, a single derrick might hoist dozens of beams in a morning, each one slotted into place before the next arrived. Mistakes had no margin. If a beam swung too far or a cable slipped, the entire site could grind to a halt while the crew reset the lines or, worse, untangled a jammed drum. The street below stayed in motion, delivery wagons queued up, clerks checked manifests, and the next beam was readied for the climb. Above, the derrick's boom traced its arc again and again, wire rope humming under tension, steam exhaust curling into the city air. Every skyscraper's skeleton rose on this choreography of gears, cables, and human judgment as hoist operators and riggers worked in sync to lift the city skyward, one beam at a time. A skyscraper's skeleton is only as strong as its connections, and in the 19-teens, those connections were forged by hand, one red-hot rivet at a time. At the heart of every steel floor, a four-man rivet crew worked in a rhythm that was half mechanical, half dance. Each man had a role. The heater crouched beside a portable forge, tending a bed of glowing coal. He watched the color of the rivets. Dull cherry red meant not hot enough. Bright yellow-white meant they would burn out. When the temperature was right, he plucked a rivet from the coals with tongs and called out. The pitcher, standing ready, snatched the rivet and with a practiced flick, hurled it through open air, sometimes 20, even 30 feet, toward the waiting catcher perched on the steel frame above. The rivet, still blazing hot, arced through wind and dust. Drop it and the process stopped cold. Miss the timing and the rivet cooled too much to use. The catcher, hands shielded by leather gloves, grabbed the glowing bolt in midair and jammed it into the waiting hole before the heat faded. Seconds mattered. If the rivet lost its color, it was useless, too stiff to deform, too brittle to hold. Then came the basher, sometimes called the bucker or gunman. He pressed a heavy steel bar against the tail of the rivet, bracing his whole body for the blow. On the other side of the beam, a partner wielded a pneumatic hammer, a roaring, rattling tool that drove the rivet's head flat against the steel. The sound was unmistakable, a rapid-fire clatter that echoed off the city blocks, floor after floor, day after day. Thousands of times per floor, the cycle repeated. Heat, throw, catch, hammer. Each rivet had to be set before it cooled, often in less than 30 seconds. If the wind picked up or the sun ducked behind clouds, the cooling sped up. On cold days, crews worked even faster, sometimes tossing rivets that steamed in the winter air. A single floor could require 10,000 rivets or more. On the Woolworth building, records show entire teams working in tandem, leapfrogging from beam to beam, each crew responsible for its own section of the growing frame. There was no room for error. A missed catch could mean a dangerous scramble to retrieve a hot rivet before it burned through clothing or skin. A poorly set rivet could weaken the entire structure. The pressure was relentless, not just from the foreman urging speed, but from the laws of physics. The steel frame could only be locked tight while the rivets were hot enough to deform. This choreography unfolded hundreds of feet above the street, without safety nets or harnesses. The men moved with a kind of unspoken trust, each relying on the others to keep the tempo. Their work was visible in the lattice of mushroom-headed rivets that still hold these towers together a century later. Each connection was a testament to seconds of perfect timing and teamwork, fusing the building's skeleton into a single unyielding whole. At the heart of every skyscraper build, communication was as critical as steel. Without radios or telephones, foremen and signalmen relied on a code of whistles, hand signals, and shouts that had to pierce through the roar of steam engines and city traffic. A single blast from a whistle could mean lift, lower, or stop. But if the sound was lost in the wind or drowned by the street below, the consequences rippled up and down the frame. On busy mornings, a missed cue between the man at the hoist and the crew on the beams could stop all lifting for an hour or more, as loads hung in mid-air and workers waited for the right signal to try again. In a 1911 account, a misread whistle nearly sent a steel beam swinging into a scaffold crowded with masons, forcing a scramble to clear the deck and costing the site half a day's progress. The pressure fell hardest on the foreman, perched between the urgency of the developer and the reality of men and machines. Every minute lost to confusion meant wages paid for idle hands, and a schedule slipping further behind. In the world of skyscraper construction without elevators, the weakest link was often not the steel or the derrick, but the fragile thread of human communication stretched to its limit. No matter how many men crowded a site or how fast derricks could swing steel, the pace of skyscraper construction always ran into the same unyielding barrier: physics. Concrete, essential for floors and fireproofing, didn't care about deadlines. Each new slab poured onto the steel frame needed days, sometimes more than a week, to cure hard enough for crews to move upward. Schedulers kept thick charts tracking every floor's progress, mapping out when a new level could safely support its own weight. If the concrete was rushed, it could crack under the strain of the next load, risking disaster and months of rework. Even the most aggressive developers, flush with cash and ambition, found themselves at the mercy of these invisible clocks. On a project like the Woolworth building, the frame might leap ahead in a matter of months, but the entire build still stretched to 2 or 3 years. The same laws that governed cooling rivets and curing concrete set the ultimate tempo. Schedulers learned to build these intervals into every chart, planning around the slow, steady tick of chemical change. No amount of manpower or money could bend these rules. When the stopwatch belonged to science, patience was the only way forward. The next time you walk beneath a city skyline, remember, the foundations of modern life rest on systems built by hand, muscle, and mind, long before automation or advanced safety standards. Today, our buildings rise faster, but often at a greater distance from those who raised them. The ingenuity and risk of those early builders still shape every city block. What will our skylines say about us?